Good morning, guys. So today we are going to look at least one problem, hopefully two, that are these are situations, problems, situations that are dealt with in the homework problem set. We're going to take a look at these problems in a general way, and look at how conservation of energy and conservation of momentum, or conservation of momentum and conservation or lack of conservation of energy can be used simultaneously to approach a problem. So the first problem we're going to look at is called the ballistic pendulum. And ballistics are high-speed projectiles. And devices like this, before the invention of high-speed cameras, devices like this, ballistic pendulums, pendula, were actually used to estimate the velocity of high-speed projectiles. And the way it works is you have a pendulum that's a solid mass. You fire a bullet at it, and the bullet gets lodged in the pendulum, but it imparts momentum and some of its energy to this pendulum, and it swings up. And it's moving much more slowly, so you can measure how high it goes, and from its final height, you can determine how fast the bullet was traveling right before it struck the pendulum. And so, just using physics and no high-speed electronics or cameras necessary. All right, so we're going to take a look at that, and then if we have time, we'll look at, well, what happens if you have two pendula that are swinging into each other elastically and colliding off one another? So these are like the pendula you would find in a Newton's cradle. All right, but just two of them, not many of them, just two of them. All right, hope you enjoyed my jokes. In the comments, in the chat. Yes, these are definitely dad jokes. The best part about being a dad is, well, I shouldn't say the best part. A good part about being a dad is you can embrace your dadness and tell what cheesy, get that? Cheesy dad jokes. All right. Ballistic pendulum. All right, so it looks something like this. You got a projectile, so a bullet that's traveling at high speed. We'll call that V, and it's traveling toward this pendulum, which consists of a big mass suspended from somewhere. And so before the collision, let's call the mass of the bullet little m, the mass of the pendulum big M, instead of using subscript. And so this is the before picture. And then after, you have something like this, where the bullet embeds in the pendulum, causing the pendulum to swing to some maximum height. So now the bullet is in here, and the pendulum has swung up. So it was down here, and now it has elevated, its center of mass has been elevated some distance. Let's call that y. All right, and so in order to, and the goal usually in this case is to figure out v, the velocity of the bullet before the collision, because it's traveling very quickly, too quickly to see, so you're going to this is one of the amazing things about physics. You can infer facts about the physical world even if you can't observe them, by measuring other observables and applying the rules of physics to calculate new quantities. Okay, so we're going to infer velocity v, little v, from how high the pendulum block swang after the collision. Okay, so this is after. And really, maybe I should call this, let's actually call this final, because immediately after the collision, the situation you have is something like this. The bullet gets embedded in the pendulum, and now the mass of the system is little m plus big M, and the whole thing is moving at some new speed, v prime. Okay, and I'm going to erase this because I didn't draw it very well. There we go, that's much better. So and then after it's now traveling with some new speed, it raises to some new height, y. So this is after the collision, but then the final position is elevated somewhere. So if you think about this problem, there's two parts. There's the part of what happens to the pendulum after the collision, and to analyze this part, we will assume frictional interactions and air resistance are all negligible. So we can take a look at this part from a perspective of conservation of mechanical energy. The change in mechanical energy equals 0. So we have some initial kinetic energy equal to 1/2 times the mass of the, didn't mean to erase, 1/2 times the mass of the system, which is now the combined mass, little m plus big M, times the velocity, the post-collision velocity, which is v prime squared. And then when it reaches its maximum height, that kinetic energy has become gravitational potential energy, equal to the mass of the system times g, that's the weight of the pendulum and bullet together, multiplied by how high it goes. So for the second part of this problem, these two things are equal to one another. All right, and so let's set them equal to one another and simplify a little bit. So this is v prime, that's my preferred, although somewhat clunky notation for the velocity of the block, the pendulum, and the bullet immediately after the collision. And so we see, one thing we see here, which we saw in the last unit, is the mass is on both sides of this energy equation, so it'll cancel and go away. And we can actually solve then for v prime, which becomes just a function of how high the mass went. So v prime, the pendulum went, is going to be the square root of 2 times g times y, how high the pendulum rose after the collision. Okay, so all of that is, that's all stuff that is from the last unit. We haven't used any conservation of momentum yet. This is just, after the collision, from that point forward, energy is conserved. Now, during the collision itself, energy is definitely not conserved because there's a lot of energy that's dissipated as heat and deformation and sound and all these other things during the collision between the bullet and the pendulum. Alrighty, so change colors here, and now let's take a look at the before to immediately after the collision. And this is what kind of collision is this? Do you know? It's a completely inelastic collision between two objects, two objects become one, completely inelastic, but nevertheless, momentum is conserved during this collision. So we could say that, before the collision, the momentum of the system is, well, the pendulum's at rest, so it doesn't have any momentum. The momentum of the system is all in the bullet. So before the collision, the momentum of the system is m times v, and then after the collision, I probably should, up here, these are vector quantities, momentums that is. So to the right is positive. So P before the collision is equal to m times v, which is just m times the magnitude of v to the right is positive, m times v. And then the momentum after is equal to, now the two masses have become one, so the momentum is the total mass times v prime, the speed after. And again, the pendulum and the bullet combined are moving to the right, which I call the positive direction. So we can write that just as a magnitude v prime, positive v prime. And these two things are equal to one another. So we have mv equals m plus m v prime. And then we can put these two things together. Plug the solution for v prime into this expression over here, and we put the two worlds together. And we get mv equals m plus capital M square root of 2gy. And let's just divide both sides by m, to get a final answer, because usually what you're after is v, the pre-collision speed of the projectile, the bullet, the ballistic let me get this. Okay. So let's take a look at this equation a little bit conceptually and ask, well, how does the system behave for different parameters? If the bullet is traveling faster before the collision, everything else being equal, the pendulum will rise higher after the bullet gets embedded in the collision. If v is large, I wonder if you can see my mouse. I think you can, yeah. If v is large, y must be large too, but it's a square root dependence. So if v doubles, y increases by a factor of square root of 2. What about the mass? Well, typically the mass of the bullet is much less than the mass of the pendulum, but if you increase the mass of the pendulum, that should decrease the vertical height, because this is in the numerator and this is, well, they're both in the numerator. So if m gets bigger, y has to get smaller for a given incoming bullet speed. If the bullet is more massive, so if m is bigger, this is a little bit harder to figure out because it's in numerator and denominator, but it's going to, if m is larger, that means y has to get larger too. because this is in the numerator and this is in the denominator, and here it doesn't matter that much because it's small compared to big M. All right, so let's pause there, and if you guys have some questions about this, you can put it in the chat. And you know, I like problems like this. You know, wink, wink. I like problems like this for assessing your understanding of momentum, because it's not just momentum. In order to understand the physics of the ballistic pendulum, you're using physical understanding from momentum, but also conservation of mechanical energy. It's really like a you know, I guess you could think of it as a two-part problem, and you put the two parts together. The first part is the collision, which itself has a before and after moment, and then the second part is the pendulum swinging up to some maximum height. And of course, it's not going to stay there unless there's some sort of you know, mechanism that holds it up there, which sometimes ballistic pendula have. But it's going to go up to some maximum height, and then it's going to swing back down. But the idea is, if you know, you imagine before high-speed electronics and high-speed cameras and stuff like that, if you're trying to measure the speed of a bullet, you could do it this way just with your eyeballs. You could get an estimate, because the pendulum would swing much slower than the bullet's traveling, and you could estimate how high it goes just with your eyeballs and a ruler. All right, I don't see any questions in the chat, so let's move on to the next scenario. Okay. And let me remind you, you know, these problems are, these situations are covered in the homework. There's a problem in the homework about a ballistic pendulum. There's actually two problems which are this kind of problem. The second one is not a pendulum, but it's a block on a table, and a bullet gets embedded in this block and it slides across the table. So in that case, you would quantify how much energy the block had after the collision, not by using conservation of mechanical energy, but by figuring out how much energy is dissipated by friction as it slides across the table until it comes to rest. Okay? So that's the work energy theorem. Change in kinetic energy equals work done by friction. Okay, in that case. So there was a, you know, in the last exam, there was a problem which had you use that physics. Okay. All right. So the second scenario involves, let's call this, there's not really a name that I'm aware of for this type of system, but let's just call it an elastic pendulum. It's like the Newton's cradle. So what you have is you have one pendulum that kind of you can pull back to some starting position, and then the other pendulum is just waiting down here at rest. And then you release the pendulum, so A swings down and collides with B. That's a horrible circle. So they collide, and then after the collision they do something. And there's actually, let's see, there's at least 3 different possibilities for what A does after the collision. But let me just draw one of them. How about I draw this one? So initially what you have is A traveling with some speed V. Wait, not there. I drew it the wrong place. right before the collision, A is traveling with some speed, call that VA, and then after the collision, the pendula swing up to some, so here's where they collided. So right after the collision, the way I drew it here, VA, pendulum A is traveling to the left, and pendulum B is traveling to the right, and then they swing up to some height called YB, YA. Put primes there. And of course over here, A starts out from some height. Call it YA. Okay. So that's a little messy. But hopefully you get the idea of what's going on here. You make this other V a blue V. So all my V's are blue. And we'll call this direction the positive X direction. Okay. So you have this pendulum A, which is elevated some initial height, YA, and then released from rest. It swings down, it collides with pendulum B, and then this collision is elastic, completely elastic, and then the two pendula swing in opposite directions after they collide. A goes back toward the left, and B swings to the right. And I said there's three different possibilities for what A does after the collision. This is one of them. Another possibility is A keeps swinging to the left. Sorry, A keeps swinging to the right, but at a reduced speed, because it imparts some of its energy to B, some of its momentum on B. Another possibility is A comes to rest. And so that's the situation that happens with Newton's cradle. And that's a special case which will happen when A and B have the same mass. Okay, but that doesn't necessarily have to be true. A and B can be the same, they could be different in terms of mass. All right. So while I'm thinking about it, we'll write that out on here. So these two pendula have masses MA and MB. Okay. So this has a part before the collision here, which is a conservation of energy part. And so what you have is you have a situation where you start out with giving A some gravitational potential energy. So the energy that you start out with here by elevating A is MA YA. I'll write it like this. It's the weight of pendulum A, MA times G, times its initial height, YA. And then when you release that pendulum and it swings down, right before it collides with pendulum B, that energy has become kinetic energy. So the mechanical energy it starts with is the mechanical energy it has right before the collision with B. 1/2 MA VA squared. So again, there's the M on both sides, it cancels. And so let's write this as the thing that's important. It's going to influence the dynamics. So what happens during and after the collision is the V. How fast is V? How fast is pendulum A traveling when it collides with B? So just like in the last problem, which was, well, we were looking at after the collision, but the speed of this pendulum, the instant before it collides with the other one, B, is the square root of 2 times g times its initial height, ya. So if you raise the pendulum higher, you give it more energy, and of course that means it's going to be swinging faster, it's going to be traveling faster when it collides with B. Not shocking. All right. Then after the collision, well, let's think about during the collision now. So during the collision here, you have the moment right before the collision, and then right after, and momentum is conserved. So the change in momentum of the system is 0. And so before the collision, it's all one-dimensional here. Everything, right before the collision, everything's moving left or right. Well, everything's moving right. A is the only thing moving. And it's moving to the right, which we said is the positive direction. So right before the collision, the momentum of the system is all with A. And it's equal to its mass times its speed, or its velocity. And it's positive because it's going toward the right, and I said that direction is positive. Right after the collision, now there is, if we look at, we got to feed in what we're assuming over here. So our assumption was that A is moving to the left. All right, that assumption means that when we write out an equation for momentum, A has now negative momentum because we said right is positive, that makes left negative. And B has positive momentum. So we got to write that negative sign in here. So the momentum of A after the collision is its mass times its speed, VA prime, when it's negative because it's going to the left. And then the second pendulum, B, has momentum MB, VB prime. Okay. And these two are equal to one another. The change in momentum is 0, so P after minus P before is 0, which means they're equal to one another. So we can write that out. MAVA was minus MA VA prime plus MB VB prime. Okay, and we know what VA is from the first part. Well, we know what VA will be. It's a function of YA. It's a function of how high it was initially elevated. So we could put that in there. Well, let's do it. So we feed this into this expression, and we get MA times the square root of 2G AY equals minus the momentum of A after the collision, because we assume it's going to the left, plus MB VB prime. Okay. So let's look at this. So what's the problem here? If we look at this expression that we get from conservation of momentum, what's the problem here? You know, typically, you know, things that you can measure are the initial height of the pendulum before you drop it, and the masses of the pendulum balls A and B. And you look at this, and the things that aren't determined then are, well, what's happening in the after case, VA prime and VB prime. And so you have two equations, you have two unknowns in this equation, and this is the way it'll be set up for you in the homework problem as well. It'll be, figure out what VA prime and VB prime are, or actually it'll tell you, well, once you know what VA prime is, you can figure out how high that pendulum swings after the collision using conservation of energy. The same for VB prime. Once you know that, you can figure out YB prime. It's a conservation of energy. It's basically this first part over here in reverse. Okay. So what do you gotta? If you have an equation, algebraic equation with two unknowns, you can't solve it. What do you need? If you have two unknowns, and so in this case, VA prime, VB prime, the post-collision velocities of these two things. What else do you need to know? Or maybe you can tell me what is the other thing that we know about the physics of this collision that we haven't used yet. Oh boy. Yesterday I got my first real professional haircut since the beginning of the pandemic. It was amazing. Oh, felt so good. Does anybody know what is the physics we're not using? Okay, I got an answer here from Holly. Let me see. Holly says, "Don't A and B have the same momentum, just in different directions? Could we use that?" So let's unpack that a little bit. So what we do know is that the total momentum of the system is the same before and after they collide. And what you're getting at here, Holly, is that the consequence of that, which we talked about last time, last time, is that means the impulse, the change in momentum that A experiences is equal in magnitude but opposite in direction to the change in momentum that B experiences. But we're already using that physics in this problem because the consequence, this right here is the consequence of that physics. If A experiences a positive change in momentum, B experiences a negative change in momentum, that's the same magnitude, so the total change in momentum is 0. So we're already using that physics. But let me pan over here a little bit. We'll focus on a word, and let's see if this gives you an idea of where I'm going. So there's some physics that we're not using yet in this problem. The collision is an elastic collision. What does that tell us? Holly says she found it. Yeah, okay. You're on the right track now, Holly. So if it's an elastic collision, mechanical energy is also conserved. Okay? So the total mechanical energy of the system is conserved. that means, there you go. So Holly wrote it out in the chat. The consequence of this, last time we wrote out, well, that means, 1/2 mv squared plus 1/2 mv squared, blah, 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 blah. You write out an expression for the total kinetic energy before the collision, and that equals the total kinetic energy after the collision. But when you algebraically simplify that expression, what you get is this idea that the relative, I'm going to write it like this, the relative velocity VA minus VB before the collision is equal to the negative of that relative velocity after the collision. And of course, if you have a negative of a difference, it's like flipping the order of that difference. So the way I wrote it last time was, sorry, I'm getting a little sloppy here, VA minus VB, so the relative velocity of the pendula before the collision, I forgot the primes here, is equal to the reverse of the relative velocities after the collision. And so this now we can use to solve for VA prime and VB prime, because now we have two equations with two unknowns. It's all one-dimensional here, so if you get the signs right, the vector notation in that second formula, you can just ignore and replace with positive or negative signs. All right, and so the reason, the relative velocity of A relative to B is, you got these two things, and the pendulum A is swinging down, it's going to collide with pendulum B. So before the collision, they're getting closer together. Right, you see that? And then after the collision, they're getting further apart. So the velocity at which they converge before is the opposite of the velocity with which they diverge after. Okay? That's what the flipping the order of those terms in this expression means. Okay. So we'll leave it at that. And I think that, let's take a look at the actual homework problems that are assigned before we call it a day. But you should be able to. So when you do these problems, don't just skip to the end. These formulas that I'm writing down for the end solution. Practice going through all the steps, because in an exam situation, I don't give you, I don't give you this. Oh, I closed it. Hold on. Darn it. I don't give you, oh, come on. Come on. There we go. So, I don't give you what's in the blue box here. What I give you is that for completely inelastic collisions, the total momentum is conserved, and the post-collision mass is that, the two objects have become one. So these are the fundamental first principles that you know. And after the collision, I don't tell you this stuff. I tell you that the mechanical energy is conserved. So you write out these expressions, and then this is derived. This is derived in the question. This is problem specific. Don't memorize stuff like this. Memorize the first principles, which is the principle of momentum conservation, and in certain situations, energy conservation as well, mechanical energy conservation. And you practice doing it. Okay, practice doing it in the homework. All right. So bear with me a second while I open up WebAssign. Wrong browser, hold on. There we go. Okay. We'll get the view that you have. And this first problem, this interactive video vignette, deals with the concept of center of mass, and it's another way that you can think about collisions and momentum is that the momentum of the system's center of mass is unchanged, so it has you just do some calculations of how, if you got two masses, how you find the center of mass. It's a weighted sum. All right. There. So here is the ballistic. Well, it's in many ways like the ballistic pendulum. The bullet comes in, gets embedded in this block, but instead of swinging up like a pendulum, it slides across this table. And it wants you to figure out, actually, never mind, it's not exactly like I described earlier. It wants you to figure out the post-collision velocity of the system. So this is a completely inelastic collision, and you don't have to use anything involving energy to solve this problem, okay? It's a frictionless table, so the bullet will collide with this block, it will start sliding, and to figure out how fast it's sliding, you just use conservation of momentum. And for a completely inelastic collision. So the post-collision mass is little m plus big M. Make sure you convert so you have common units of kilograms. So this is an impulse question, okay? So this is the impulse experienced by the golf club is equal to the negative impulse experienced by the golf ball. Okay, maybe we'll take a closer look at that during Friday's recitation if anyone has any questions about it. So here's the ballistic pendulum question. Okay, one of the complications here is it wants you to enter velocities as in relative terms. The velocity of the pendulum system after the collision is some multiple of the initial velocity, and the same for mass. Okay, so it's just entering, not algebraic well, these are algebraic answers, but the number you're entering here is the coefficient. What's the relationship between big V and little v, big M and little m? This is a tutorial question, so if you click on, you can't see the window that opened, but if you click this button, there's a tutorial that will walk you through this problem, break it down into smaller steps. Those are very useful. Here's the elastic pendulum, the problem that we were just considering, and you're asked to figure out what's the post-collision velocity of each of these balls, exactly what we were just talking about. All right. This problem right here is pretty hard. This is a pretty hard problem. Remember I said, oh, I didn't even enter an answer there for that yet. But remember I said I would be doing a tutorial video. So that's the tutorial video I'll be doing and posting. And it's a challenging problem because, I mean, you can end up with a system of equations where there's it turns out that there's 3 unknowns in this problem. So you have 3 equations that you can solve, but there's trig functions in there. It's an algebraic nightmare, but I don't know, I've said this before, we haven't really done this too much, but one of the very powerful techniques that you can apply to finding solutions in physics is simplifying assumptions. Well, we do this all the time when we assume that friction is negligible, that sort of thing. But in this case, there is a simplifying assumption that, well, actually 2 simplifying assumptions that you can make, and they both are result from the fact that you have a collision between 2 objects where the incoming object is a helium nucleus and the target is a gold nucleus, and there's this huge mass disparity between those 2 objects. The helium nucleus is much less massive. The ratio is well, the helium nucleus has 4 protons and neutrons, a total of 4 protons and neutrons, and the gold nucleus has 197 protons and neutrons. So that's a huge disparity, almost 50 times more massive. And so you can leverage that disparity to make a simplifying assumption, which basically makes this problem a breeze. Well, still not a breeze. There's still some algebra to do and trig functions to contend with. But I'll post a tutorial on this question, which you can follow and find your answer. All right. So that's it for today. Any questions before we stop for the day? Let me see. Checking the chat window. I don't see any. I'll pause for a minute if you have any. So this homework is due Monday, November 2nd, and that's still my target for this. Okay. So Friday we will do recitation in person. Please come. You know, I think that the students who come to the recitation, I think you guys are getting a lot out of that. It's just really high impact, and I think that the students who come just really benefit. But I'll strive to Zoom it live as well. Okay. Thank you, Holly. I'm glad I got a professional haircut too. All right. I'll see you guys on Friday.